So this is another um, very powerful theorem in complex variables, and it's called the theorem of analytic continuation. So the idea is very simple. We have looked at analytic functions that can be analytic over a region in the complex space. They do not have to be, they may not be analytic all over the plane. So think of a function f1z which is analytic over this region R1, and think of another function f2z which is analytic in this region R2, where R1 and R2 have an overlap which we call R. So this is the overlap region, and in this overlap region f1z is equal to f2z. So I have an analytic function f1z here, I have an analytic function f2z here. uh, if this is the case that f1z is f2z in the intersection region, then the function fz, which is f1z in R1 and f2z is in R2, is uh, well, in that case f2z is called the analytic continuation of f1z into R2, and f1z is called the analytic continuation of f2z in R1. So we can find analytic chain of analytic functions, and we can define a composite function fz. We can patch together a composite function fz which is analytic over a much larger region than either R1 or R2. We are going to use this idea um, very carefully for a set of problems which are half plane problems. And these are very important for solving problems in cracks, in cracked bodies. Uh, so you need to understand this idea of analytic continuation very carefully. Let me give you a couple of examples. For example, e to the power z, e to the power z um, analytically continues e to the power x from the from R1, which is the real axis, into the entire complex plane. So when the imaginary part of z is equal to 0, that means you are on the real axis, then ez becomes ex, which is this series, and then uh, ez continues this series from the real axis into the entire complex plane. A more non-trivial example is this series here, and we know for mod z less than 1, this series converges to 1 by 1 minus z. Okay, so if you have, this is the imaginary and real axis, so uh, if you have this disk centered at the origin and radius 1, inside this disk f1 is equal to f2, whereas f2z is analytic everywhere except at this point. F2z is analytic everywhere. So f2z will be analytically continues this function to the entire complex plane except for this point, except for this point. Okay, so these are examples by which you can take a function which has a particular take functions that look very different from each other and patch them together to create an analytic function. How is it useful to us? It is useful to us for simplifying the km equations in half plane problems. So half plane problems, before we do that, let us define two kinds of limits. So uh, this is my real axis and this is my imaginary axis. So I have a function fz here. Okay, so when I approach the real axis from top, that means y tends to 0 plus, fz will tend to fx, and since it's tending to from the above, I'll call it f plus x. So this is the limit that I will use. When I say f plus x, it will mean that z is tending to the real axis from above. When it is tending to the real axis from below, then fz will tend to fx again, but we'll call it f minus x because it tends from below. And now half plane problems are problems that are defined in this plane, which we are going to call S plus, and this plane will be called S minus. So my body lies in S plus, and I will use the idea of analytic continuation and these two limits f plus x and f minus x in order to simplify the km equations in S plus. Okay, you have to remember that there's nothing here, there's no body here, so this is y less than 0 and this is y greater than 0. The body actually lies in the upper half plane, which is y equal to 0. Now let us start with the case where the body lies here and this plane is traction free. If this plane is traction free, the normal to this plane is this. So if it's traction free, that means that sigma yy plus I sigma xy is equal to 0. So on this plane, on y equal to 0, this is the situation. So let us use that. We can also write it as, since it's 0, we can write this as sigma yy minus I sigma xy. We write it as sigma yy minus I sigma xy because from the km equations, this quantity is easier to determine. Let's see how it is done. Sigma xx plus sigma yy is, remember, equal to 2 omega prime plus omega prime bar, and then sigma xx minus sigma yy plus sorry, oops, sorry, I did something wrong. So sigma xx plus sigma yy plus 2I sigma xy is equal to minus 2z omega double prime bar plus small omega prime bar. So this is what we have. So we want sigma yy and xy, so we subtract these two. If we subtract this two, we subtract this plus minus, and then we get sigma yy minus I sigma xy is equal to plus z. So this is what we get, and this thing is equal to 0 as y tends 0 plus, which means you are approaching the real axis from above, which is what you should do because your body lies above. So when you do that, when you take limit y tends to 0 plus of this, here you have, this is a function of z, so you are approaching from above, so it will become omega prime plus x. This will become omega prime plus x bar. This will become x omega double prime plus x bar, and this will become small omega prime plus x bar. This is what it will become. This will be, the sum of this will be equal to 0. So I can write omega prime plus to be negative of this, sorry, negative of this, and this. So that's what I've done. So this is the equation that I get when y approaches 0 plus. Now what I am going to do is I will try and cook up a function which will lead to the same value of omega plus prime when approached from below. So that is what I'm going to do now. So this is the function. So remember, this is my imaginary axis, real axis. The body lies here, and earlier I was approaching from here. Now I cook up this function theta prime z, which is uh, minus omega prime z minus z omega double prime z and small omega prime z. This function is analytic in S plus because all these guys are analytic in S plus. So this also has to be analytic in S plus. If this is analytic in S plus, then I can define a associated function of this. Remember, associated function is defined by taking z bar and then taking the bar. This is the associated function. And we have seen earlier that if this is analytic in S plus, the associated function is analytic in S minus. So this function is now analytic in S minus. This function is analytic in S minus. And if I take associated function of this, I'll take associated function of this, this, and this. And now if I take the limit as y, limit from below as y tends to 0 minus, y tends to 0 minus of this function, what I get is this will now be omega x, but you have z bar here, you are approaching from negative side, so this is minus. So you are approaching from y tending to 0 minus, but this is z bar here. When you approach z bar from y equal to 0 minus, you are actually approaching from here because z bar is x minus iy. You have a negative here. When y is approaching 0 from the negative side, minus iy is approaching 0 from the positive side. So this, because of this z bar here, this will lead to omega prime plus. This will lead to x omega double prime. Again, you have z bar here. When you are approaching from below, z bar approaches the real axis from the top. So this will be this plus, and this will be. So the limit y tends to 0 minus of theta of the associated function of theta prime is same as the limit that you got for uh, capital omega prime. This is the same. So on the real axis, uh, this function and this function coincide, so they are the same. So one can be used as an analytic continuation of the other over the entire plane s plus plus s minus. So I can now define a new function. Omega z, which is, oh, sorry, there's one more step here. So that is this. So I have proved that limit approach from above of omega prime z is limit approach from below of the associated function of theta prime z. Okay, now you can integrate on both sides. Remember, theta prime z, we have taken it to be theta prime z was taken to be so if you integrate on both sides, you get theta z is equal to these two together integrate as z omega prime z minus and minus omega z. So this is the integration of this, and the and here if you integrate on both sides, so you get capital omega z here, and so this was the integration of theta z. So the associated function would integrate to minus z associated function of omega prime and capital omega prime, omega and capital omega prime, and then this z, if you take z bar and then take the bar of that, you get z back. So this would be the integration of the associated function of theta, and that will be equal to capital omega z as y tends to 0. So this would be capital omega z equal to this, and um, as soon as you have this, uh, you now have a completely defined function capital omega z, which is equal to the omega z in s plus, and then is equal to this in s minus. So this function is equal to this function in s minus, where there's no body, but we have just defined the analytic continuation in s minus, and now we will do a trick. So in s minus, this is equal to minus z, this is the case in s minus, which means now in s minus omega z bar associated function of omega is equal to minus this minus z associated function of omega prime is prime. Okay, if this is the associated function in s minus, then the associated function of this is the actual function omega z. That has to be equal to the associated function of omega minus z times omega prime z. So in s plus, if this is true in s minus, this has to be true in s plus, which means that in s plus now you have a relation between omega, small omega, and capital omega, which means that for half plane problems, using analytic continuation, we can show that one km potential can actually be expressed in terms of the other. And when you do that, the km equations simplify somewhat, and you have only one potential to determine. So the km equations in that case become these. So you don't have small omega. I have removed small omega from everywhere. You get this z bar minus z, because you have removed small omega in terms of capital omega, and these are the set of km equations that have to be used for half plane problems. You can do this also if you have displacement continuity or displacement free boundaries at y equal to 0. So if you have a body where which occupies this part, and this surface is the displacement of this surface is fixed, equal to 0. If this surface has no displacements, then we can use the displacement km equations, to do the same trick with analytic continuation. So in that case, we will use the displacement. So remember, this is the displacement 2 mu d, this is 2 mu d according to km equations, and as you tend to y0 plus, this will become omega plus, this will become omega prime x bar plus, and this will become small omega plus bar. So this is equal to 0. Now define again another function, which is theta z. So this is defined in s plus. Theta z is obviously analytic in s plus, which means the associated function will be analytic in s minus. So in s minus you will have this. Take the associated function on the left side, associated functions have to be taken on the right side also. So this associated function is this associated function is this. So when you do this, now you take the limits. Limit of, so this is defined in S minus, so you have to take the limit from below. So when you take the limit from below, this becomes x, z becomes x. This z bar, if y is approaching from below, z bar is approaching the real axis from above, so this becomes this. And again, z bar is approaching from above if y is approaching from below, and this becomes this. So if you look at it, then you will see that limit y tends to 0 minus is same as limit y tends to 0 plus of this quantity. Y tends to 0 plus of this quantity was exactly these two terms taken to the right hand side, these two terms, and these two terms also appear when you take the limit y tends to 0 minus of the associated function of theta, which means that now you can analytically continue uh, analytically continue omega z into the lower half plane through the associated function of theta z. So we can now have a composite function. We've stitched together the function omega z is equal to omega z in S plus, and it continues as this function, which is the associated function of theta z in S minus. So this is what it is. So in S minus you can now write omega, the associated function of omega is equal to capital omega z kappa of capital omega z minus z associated function of omega prime z. This is analytic in S minus, which means that omega z equal to kappa associated function of this minus z is true in S plus, which means again you can eliminate omega z from the Km equations altogether, and the displacement Km equations take this form. So in either case, where displacements are specified here, or you have a half plane with traction specified, so this is a traction free surface, this is your half space in S plus. So in either of these two cases, you have simplification of the Km equations where one potential can be removed in favor of the other. We have removed small omega z, and you get a set of reduced Km equations where we will have to determine only one function rather than two. So we will stop here this week. In the next week, you need to do these derivations very carefully yourself. And if you can do that by next week, we'll apply them to solve interesting problems involving cracks and holes in infinite bodies. So let's stop here.